Hello and welcome. It's wonderful to have you here, taking a quiet moment just for yourself. Before we begin, if you enjoy calm, science-based stories that gently teach you about the universe while helping you relax, consider subscribing. Your support helps keep these peaceful, carefully researched explorations coming. Now, settle into a comfortable stillness and let your breathing soften. Tonight, you are not here to imagine distant worlds, but to quietly observe one of the most powerful structures ever measured in the universe. Light from billions of years ago travels slowly to reach us, carrying real, measurable information about mass, energy, and motion. As you listen, allow yourself to follow the data, the light, and the quiet unfolding of cosmic understanding. You settle into the idea that discovery in astronomy begins with careful attention to light that never reaches human eyes. Long before the Phoenix cluster receives a name, instruments aboard space telescopes quietly register faint X-ray photons arriving from a distant region of the southern sky. These photons carry information about gas heated to extreme temperatures, gas that shines not in visible colors but in high-energy radiation. You follow how astronomers notice this signal during systematic sky surveys designed to map large regions evenly, without targeting anything unusual. The source appears persistent, extended, and remarkably bright for its distance. You remain aware that distance in astronomy is measured through redshift, a stretching of light caused by the expansion of space itself. Optical telescopes observe galaxies in the same region, and their spectra show that their light has shifted toward longer wavelengths by a consistent amount. This shared redshift tells you that the galaxies and the X-ray emission belong to the same physical structure. You understand that seeing objects billions of light-years away means observing the universe as it was long before Earth existed, when large structures were still assembling. You notice that galaxy clusters are rarely identified through visible light alone. Individual galaxies are small points compared to the vast spaces between them, and their combined starlight fades with distance. Instead, the most reliable signal comes from the intracluster medium, a thin plasma filling the space between galaxies. As gravity pulls matter together, this gas compresses and heats to tens of millions of degrees. At such temperatures, atoms lose electrons and emit X-rays through well-understood physical processes. You take comfort in knowing that these emissions follow predictable laws tested in laboratories and observed throughout the universe. You follow the careful steps scientists use to confirm that the source is not something else, such as a single active galaxy or a closer object along the same line of sight. Observations across different wavelengths are compared, and the size of the X-ray glow is measured precisely. It extends across millions of light-years, far larger than any individual galaxy could produce. When light from visible galaxies is digitally removed, the X-ray emission remains, showing that the radiation comes from diffuse gas rather than compact sources. Each test reduces uncertainty and narrows the explanation. You learn that the Phoenix cluster stands out immediately because of its power. For its measured distance, it emits more X-rays than nearly any other known cluster. This brightness suggests a deep gravitational well capable of holding vast amounts of hot gas. You understand that X-ray brightness depends on both temperature and density, meaning this cluster is not only hot but unusually dense near its center. These conclusions are not guesses. They are calculated using calibrated detectors, repeated measurements, and physical models refined over decades. You remain grounded in the understanding that discovery is rarely sudden. Data from multiple observatories are combined, checked, and reanalyzed over time. Ground-based telescopes map the positions and motions of hundreds of member galaxies. Their velocities show that they are bound together by gravity, moving within a shared gravitational potential. The range of these velocities provides another measure of mass, independent from X-ray data. Agreement between methods strengthens confidence, while small differences encourage further examination rather than dramatic claims. You notice how the cluster earns its name only after its properties are verified. Located in the constellation Phoenix, it becomes associated with a mythological bird in name alone. The explanation remains entirely physical, grounded in gravity, thermodynamics, and radiation. You stay aware that naming is a human convenience, while the object itself exists independently of stories or symbols. You reflect on how astronomical surveys have transformed understanding from isolated discoveries into comprehensive maps. Instruments scan the sky methodically, building catalogs that allow rare objects to be identified statistically. The Phoenix cluster emerges from these catalogs because it occupies an extreme position among known clusters. You understand that rarity becomes a measurable property, defined through comparison rather than impression. You stay with the role of space-based observatories operating above Earth's atmosphere, where X-rays can be detected without interference from air. Satellites equipped with precisely shaped mirrors guide high-energy photons toward sensitive detectors. From these measurements, temperature maps are constructed, revealing how heat is distributed across the cluster. You appreciate that each map forms from countless detections collected patiently over long periods and analyzed using transparent methods. You also notice how optical imaging adds essential context. Deep observations reveal a dense concentration of galaxies, many appearing redder due to distance and older stellar populations. Spectroscopic measurements provide precise redshifts, confirming that these galaxies share a common location in space. You understand that combining independent techniques reduces uncertainty, because each responds to different physical properties. When the results align, confidence grows steadily. You rest with the understanding that such discoveries depend on collaboration and verification. Data are shared openly, assumptions are tested carefully, and uncertainties are reported clearly. Nothing about the Phoenix cluster rests on a single image or interpretation. Its presence emerges from repeated, consistent measurements that align with established physical laws. In this steady accumulation of evidence, you sense how observation naturally opens deeper questions about mass, heat, and the forces shaping the largest structures in the universe. As distant X-ray photons continue their quiet arrival, you remain aware that careful measurement does more than reveal what exists. It also hints at why certain places in the universe behave in ways that invite closer attention. You rest with the understanding that location in the universe is never simple placement on a map. To know where the Phoenix cluster sits, you rely on light that has traveled for billions of years, carrying with it a record of expanding space. The galaxies within the cluster do not merely appear faint. Their light is stretched, shifted toward redder wavelengths in a measurable way. This redshift is not caused by motion through space alone, but by space itself growing larger during the journey of the light. You recognize this as one of the most tested observations in modern cosmology. You allow your attention to settle on how astronomers translate redshift into distance. Spectral lines from known elements, such as hydrogen and calcium, appear at predictable wavelengths when measured in laboratories. In distant galaxies, these same lines appear shifted by a precise fraction. That fraction corresponds to how much the universe has expanded since the light was emitted. You understand that this method does not depend on brightness or assumptions about size. It relies on atomic physics that behaves the same everywhere it has been tested. You follow how the Phoenix cluster is measured to lie more than 5 billion light-years away. This means the light reaching Earth began its journey when the universe was significantly younger than it is now. You are not only learning where the cluster is, but when it is. Distance becomes a form of time travel grounded in observation rather than imagination. The cluster you observe exists as it was long before the Sun formed, during an era when large structures were still actively evolving. You remain aware that the universe is not arranged randomly on large scales. Galaxies and clusters trace long filaments separated by vast voids, forming a pattern often described as the cosmic web. This structure emerges naturally from the growth of tiny density variations present in the early universe, variations measured precisely in the cosmic microwave background. Gravity amplifies these small differences over billions of years, pulling matter into sheets, filaments, and nodes where clusters form. You recognize that the Phoenix cluster occupies one of these dense nodes. You take comfort in knowing that this picture is supported by multiple lines of evidence. Large galaxy surveys map millions of galaxies, revealing repeating patterns consistent with theoretical predictions. Computer simulations using well-tested physical laws reproduce similar structures when started with early universe conditions measured independently. The placement of the Phoenix cluster aligns with these expectations, reinforcing the idea that even extreme objects arise within an ordered framework. You notice that environment matters. Clusters located at intersections of filaments tend to grow more massive by drawing in surrounding material. Gas flows along these filaments, heating as it falls into deep gravitational wells. You understand that the Phoenix cluster's surroundings may contribute to its exceptional properties. This is not stated as certainty, but as a relationship explored through observation and comparison with other clusters at similar distances. You remain grounded in the role of scale. The cluster spans several million light-years, yet this is small compared to the distances between clusters. Light traveling from one large structure to another crosses vast regions with little matter at all. You recognize that emptiness dominates the universe by volume, while mass concentrates in relatively small regions. This contrast shapes how matter evolves and how energy moves across cosmic distances. You reflect on how measuring position also involves understanding motion. The galaxies within the Phoenix cluster move relative to one another at speeds of thousands of kilometers per second. These motions are measured through small shifts in spectral lines, revealing how gravity binds the system together. The overall redshift of the cluster, however, reflects the expansion of space itself rather than internal motion. You appreciate how astronomers carefully separate these effects using well-established techniques. You stay with the idea that observing distant clusters tests cosmological models. The number of massive clusters at different distances provides constraints on how structure grows over time. The presence of an extremely massive, active cluster at this distance is rare but not contradictory to current understanding. Instead, it refines statistical models and encourages more precise measurements. You see how science advances not by surprise alone, but by careful adjustment. You settle into the calm realization that the Phoenix cluster is part of a larger narrative written across space and time. Its position reflects conditions set shortly after the universe began, shaped by gravity, expansion, and the properties of matter itself. Nothing about its location requires special assumptions. It fits within a framework tested repeatedly through observation. As you hold this perspective, you sense that knowing where something sits also hints at what influences it. Distance, time, and surrounding structure quietly shape how immense systems develop and change. You ease into the idea that a galaxy cluster is not simply a crowded group of galaxies. It is a gravitational system, defined by mass, scale, and stability rather than by how it looks in an image. Astronomers use the term only when gravity binds the system strongly enough that it will remain intact for billions of years. This distinction matters because many galaxies appear close together by chance alignment. True clusters reveal themselves through shared motion, temperature, and gravitational influence. You notice that a defining feature of any galaxy cluster is its mass. Individual galaxies, even large ones, contain only a small fraction of the total. Most of the mass exists in two other forms, hot gas and dark matter. The gas fills the space between galaxies, forming a diffuse plasma that responds directly to gravity. Dark matter, though invisible, dominates the mass budget and determines how everything else moves. You understand that without this hidden component, clusters could not exist as observed. You stay with the way gravity shapes the system. As matter falls inward, potential energy converts into heat. Gas particles accelerate, collide, and reach temperatures of tens of millions of degrees. At these temperatures, the gas emits X-rays, providing one of the clearest signatures of a cluster. This emission is not decorative. It is a direct consequence of physical laws governing charged particles. You rest with the reliability of these laws, tested in laboratories and confirmed in space. You learn that astronomers classify clusters using several complementary criteria. One involves measuring the velocities of member galaxies. Galaxies bound to a cluster move within a predictable range of speeds set by the cluster's total mass. Another involves mapping the distribution of hot gas through X-ray observations. A third uses gravitational lensing, where the cluster's mass bends background light. When these independent methods agree, the classification becomes secure. You remain aware that size matters. Galaxy clusters typically span millions of light-years and contain hundreds to thousands of galaxies. Below this scale are galaxy groups, which are smaller and less massive. The boundary between groups and clusters is not sharp, but defined statistically. You find calm in knowing that science often works with ranges and probabilities rather than rigid categories. Precision comes from careful comparison, not absolute labels. You notice how clusters represent the endpoint of structure formation on large scales. While galaxies continue to merge and evolve within clusters, clusters themselves grow slowly. The expansion of the universe limits how much additional matter they can gather. Gravity pulls inward, while cosmic expansion stretches space outward. On the scale of clusters, gravity still dominates locally, allowing them to remain bound even as space expands elsewhere. You reflect on how clusters reveal the interaction between visible and invisible matter. Galaxies trace only a small fraction of the gravitational field. When astronomers map mass using gravitational lensing, they find that dark matter forms a smooth, extended halo enveloping the entire cluster. The hot gas settles into this potential well, while galaxies orbit within it. You understand that this arrangement is not assumed. It is measured repeatedly across many systems. You stay grounded in the idea that clusters are laboratories for physics. Conditions inside them cannot be reproduced on Earth. Temperatures, scales, and energies exceed anything achievable in experiments. Yet the underlying principles remain familiar. Gravity, electromagnetism, and thermodynamics operate the same way everywhere. By observing clusters, scientists test these principles under extreme but natural conditions. You allow your attention to rest on how clusters evolve over time. Galaxies entering a cluster experience changes. Gas can be stripped away by interaction with the hot intracluster medium. Star formation may slow as fuel is removed or heated. These processes are observed directly in nearby clusters and inferred in distant ones through statistical trends. You understand that a cluster is not static, but slowly changing under well-understood influences. You remain calm with the idea that no two clusters are identical. Differences in mass, formation history, and environment lead to a wide range of behaviors. Some clusters are relatively quiet, with little new star formation. Others, like the Phoenix cluster, show signs of intense activity. These differences are not anomalies but expressions of how initial conditions and ongoing processes interact over cosmic time. You settle into the realization that defining a galaxy cluster means identifying balance. Gravity must outweigh expansion locally. Heat must reflect the depth of the gravitational well. Motion must remain bound rather than dispersing. When these conditions are met, a cluster exists as a coherent structure. This definition is not poetic or flexible. It is rooted in measurement, physics, and repeated observation. As you hold this understanding, you sense that knowing what a cluster is naturally invites attention to how much mass it contains and how that mass is measured across such immense distances. You rest with the understanding that mass cannot be placed on a scale when it belongs to something millions of light-years wide. Instead, astronomers learn to measure mass by observing its effects. Gravity leaves signatures that can be traced carefully, even across immense distances. You follow how these signatures become reliable tools when interpreted through well-tested physical laws. You begin with the motion of galaxies. Inside a massive cluster, galaxies move rapidly, pulled inward by the combined gravitational influence of everything around them. Their speeds are not guessed. They are measured through small shifts in spectral lines, caused by the Doppler effect. Light from a galaxy moving toward Earth shifts slightly toward shorter wavelengths, while light from a galaxy moving away shifts toward longer ones. By measuring these shifts precisely, astronomers calculate how fast each galaxy moves along the line of sight. You understand that faster motion implies greater mass. A shallow gravitational field cannot hold galaxies moving at thousands of kilometers per second. When many galaxies show high velocities within the same region, gravity must be strong enough to keep them bound. Mathematical relationships derived from Newtonian dynamics and refined through relativistic corrections allow scientists to convert velocity distributions into mass estimates. These calculations are applied carefully, with uncertainties clearly stated. You remain aware that galaxy motions sample only part of the cluster. Many galaxies orbit far from the center, while others move through denser regions. To gain a fuller picture, astronomers turn to the hot intracluster gas. This gas responds smoothly to gravity, settling into a shape determined by the underlying mass distribution. Its temperature and density vary with distance from the center, and these variations are measured through X-ray observations. You follow how temperature becomes a clue. Hotter gas moves faster at the particle level. When gas reaches tens of millions of degrees, it indicates that it has fallen deep into a gravitational well. The relationship between gas temperature and total mass is grounded in thermodynamics and hydrostatic equilibrium, a condition where inward gravitational force balances outward pressure from heat. While real clusters are not perfectly static, this approximation works well when applied cautiously. You notice that astronomers do not rely on a single approach. They compare mass estimates derived from galaxy motions with those derived from gas properties. When the values align, confidence increases. When they differ, the assumptions are examined and refined. This process reflects how science advances through consistency checks rather than dramatic claims. You then rest with one of the most direct methods available, gravitational lensing. Massive objects bend spacetime itself, causing light from background galaxies to follow curved paths. This bending distorts the shapes and positions of distant galaxies in subtle but measurable ways. You understand that this effect depends only on mass, regardless of whether that mass emits light. In this way, lensing provides a map of total mass, including dark matter. You follow how lensing measurements are made statistically. Individual background galaxies have random shapes, but when many are observed behind a cluster, patterns emerge. Slight stretches and alignments reveal the presence of a gravitational field. By analyzing these patterns, astronomers reconstruct how mass is distributed across the cluster. This method does not rely on assumptions about gas behavior or galaxy motion. It responds directly to gravity itself. You find calm in the way these methods converge. For the Phoenix cluster, lensing confirms the enormous mass suggested by X-ray brightness and galaxy velocities. Each technique carries its own sources of uncertainty, but their agreement strengthens the conclusion. The cluster contains hundreds of trillions of times the mass of the Sun, making it one of the most massive known structures of its kind at its distance. You remain grounded in the idea that uncertainty is always present and always acknowledged. Error bars accompany every measurement. Assumptions are tested against simulations and observations of other clusters. When models change, past measurements are revisited. This openness does not weaken conclusions. It makes them stronger. You reflect on how measuring mass also reveals composition. Only a small fraction of the total mass resides in stars within galaxies. A larger fraction exists as hot gas. The largest portion remains unseen, inferred through its gravitational influence. This consistent pattern across clusters supports the existence of dark matter as a fundamental component of the universe. You understand that this conclusion arises from repeated observation, not from preference or convenience. You stay with the realization that measuring mass on cosmic scales connects small and large. Atomic physics governs spectral lines. Classical mechanics informs motion. General relativity explains lensing. These same principles apply everywhere, from laboratories on Earth to clusters billions of light-years away. Their consistency allows confident measurement across unimaginable distances. You settle into the awareness that once mass is known, many other properties follow. Temperature, motion, and structure all relate back to gravity. Knowing how heavy something is opens the door to understanding how it behaves. As this sense of scale rests gently in your mind, you become aware that mass also governs how matter heats, moves, and fills the vast spaces within a cluster. You rest with the idea that most of a galaxy cluster is not made of galaxies at all. Between the bright points of starlight lies an enormous volume filled with thin, superheated gas known as the intracluster medium. This gas is so diffuse that it would register as an extreme vacuum by everyday standards, yet it contains more ordinary matter than all the stars in the cluster combined. You remain aware that this conclusion comes from measurement rather than assumption, built from decades of consistent observation. You notice that this gas reaches temperatures of tens of millions of degrees. Such heat does not come from stars or explosions. It arises naturally as gravity pulls matter inward. As gas falls into the deep gravitational well of a massive cluster, potential energy converts into kinetic energy. Particles accelerate, collide, and spread energy among themselves. The result is a plasma so hot that atoms cannot hold onto their electrons. You stay with the physics of this state. When electrons are stripped from atomic nuclei, the gas becomes electrically charged. These charged particles interact through electromagnetic forces, producing radiation when electrons are deflected by ions. This process, known as thermal Bremsstrahlung, emits X-rays whose intensity depends directly on temperature and density. You find comfort in how this mechanism is well understood, described precisely by equations tested in controlled experiments. You follow how space-based observatories detect this radiation. X-ray telescopes focus high-energy photons onto sensitive detectors, allowing scientists to measure both brightness and energy distribution. From these measurements, temperature maps are constructed, showing how heat varies across the cluster. In the Phoenix cluster, these maps reveal extraordinarily hot gas extending across millions of light-years, with even denser and cooler regions toward the center. You remain grounded in the idea that cooler, in this context, still means millions of degrees. Compared to the outer regions, the core gas emits X-rays at slightly lower energies, indicating slower particle motion. This difference matters because it reveals how energy moves through the system. You understand that heat flows, pressure balances gravity, and turbulence redistributes energy over time. None of this requires imagination. It follows directly from plasma physics and thermodynamics. You notice how density becomes just as important as temperature. X-ray brightness increases sharply where gas becomes denser, because more particles are available to emit radiation. In the Phoenix cluster, the central region shows an unusually high density of gas. This observation explains why the cluster appears so luminous in X-rays even at great distance. Brightness here is not a surface effect but a volume measurement integrated along the line of sight. You stay with how scientists infer mass from this gas. By measuring how density and temperature change with distance from the center, astronomers calculate the pressure gradient. Assuming the gas is roughly supported against gravity by this pressure, they derive the total gravitational mass required to maintain equilibrium. While no cluster is perfectly still, this method produces results that agree well with independent techniques. You reflect on how composition is also revealed. Spectral lines from elements such as iron, silicon, and oxygen appear in X-ray spectra. These elements were forged in stars and spread into the intracluster medium through supernova explosions over billions of years. Their presence confirms that the gas has been enriched by generations of stellar activity. You remain calm with the knowledge that even in vast, hot environments, traces of stellar history remain measurable. You understand that this gas plays an active role in shaping galaxies. As galaxies move through the intracluster medium, they encounter resistance similar to air drag, though far weaker. This interaction can strip gas from galaxies, reducing their ability to form new stars. Observations of nearby clusters show clear evidence of this process, and its effects are inferred in distant systems like the Phoenix cluster through population trends. You stay with the realization that the intracluster medium is not static. It responds to mergers, motions, and energy input from central black holes. Shock waves travel through it when clusters collide. Sound waves and turbulence distribute energy over large distances. Each of these processes leaves signatures in X-ray images, such as ripples, edges, and cavities. You understand that reading these patterns requires patience and careful modeling. You rest with the roll of time. The gas you observe has been accumulating and heating for billions of years. This current state reflects a balance between ongoing heating and gradual cooling. In most clusters, cooling is slowed or prevented by energy injected from central regions. The Phoenix cluster, however, shows signs that cooling proceeds more efficiently than usual. This observation stands out not because it is dramatic, but because it is measured consistently across multiple datasets. You remain grounded in the fact that the intracluster medium dominates how clusters appear in high-energy light. Without it, clusters would be far harder to detect at great distances. These properties reveal mass, history, and ongoing physical processes. You sense that understanding this hot plasma is essential to understanding why some clusters behave in unexpected ways. As this awareness settles, you notice that where gas becomes densest and coolest, matter begins to behave differently, opening quiet questions about how heat can sometimes escape even the strongest gravitational wells. You settle into the idea that heat, left alone, does not last forever. In any physical system, energy spreads out, and hot material gradually cools as it radiates energy away. This principle applies just as reliably to galaxy clusters as it does to everyday objects. The hot gas filling a cluster emits X-rays continuously, and each emitted photon carries energy away. Given enough time, the gas should cool, slow its motion, and drift inward under gravity. You follow how early models of clusters predicted this behavior clearly. Calculations showed that in dense central regions, the cooling time of the gas could be much shorter than the age of the universe. Cooling time is a measurable quantity, defined by how long it would take for gas to lose its thermal energy through radiation at the observed rate. In many clusters, this time is far less than 1 billion years. You understand that such predictions are grounded in well-known radiative processes, not speculation. You remain with how observations challenged these expectations. When astronomers looked for the results of cooling, they found less cold gas and fewer new stars than predicted. X-ray spectra did not show the full range of temperatures expected if gas were cooling steadily from tens of millions of degrees down to much lower values. This mismatch became known as the cooling flow problem, a discrepancy between theory and observation that persisted across many systems. You rest with the resolution that emerged gradually. Central supermassive black holes in clusters were found to inject energy back into the surrounding gas. Through jets, bubbles, and shock waves, these black holes transfer enormous amounts of energy into the intracluster medium. This feedback heats the gas, offsetting radiative cooling and preventing large amounts of gas from condensing. You understand that this explanation is supported by radio and X-ray images showing cavities and ripples aligned with black hole activity. You stay grounded in the balance involved. Cooling has not stopped entirely in most clusters. Instead, it is regulated. Gas loses energy, begins to cool, and then receives heat that slows or reverses the process. This feedback loop appears finely tuned, operating over millions of years. You recognize that this balance is inferred from repeated observations across many clusters, not from a single example. You then notice how the Phoenix cluster stands apart. Measurements show that its central gas cools at a much higher rate than in most known clusters. X-ray spectra reveal emission consistent with gas cooling through a broader range of temperatures. The inferred cooling rate reaches hundreds of solar masses per year, far exceeding typical values. You understand that this conclusion is not based on brightness alone, but on detailed spectral modeling that separates temperature components carefully. You remain aware that astronomers approach such findings with caution. Alternative explanations are tested, uncertainties are examined, and independent observations are sought. In the case of the Phoenix cluster, multiple space-based telescopes observe consistent signals. The cooling appears real, persistent, and unusually efficient. This makes the cluster an exception that sharpens understanding rather than undermines it. You reflect on why cooling is strongest in the central region. Density plays a crucial role. Radiative cooling increases with the square of particle density, meaning that even small increases in density lead to much faster energy loss. The Phoenix cluster's core contains exceptionally dense gas compared to similar systems. You understand that this density accelerates cooling, pushing the system toward behavior rarely seen elsewhere. You stay with the role of pressure and gravity. As gas cools, pressure drops, and gravity pulls material inward. This inward flow can further increase density, creating a feedback that promotes additional cooling. In most clusters, heating interrupts this cycle early. In the Phoenix cluster, the interruption appears incomplete. You recognize that this does not imply failure of physical laws, but a shift in balance between competing processes. You consider the timescales involved. Cooling does not happen instantly, even in extreme environments. The gas observed cooling today has been radiating energy for hundreds of millions of years. The current state reflects conditions averaged over long periods. You find calm in knowing that observations capture a moment within a slow, continuous process. You remain grounded in how scientists quantify these flows. Cooling rates are expressed in mass per unit time, derived from luminosity and temperature distribution. These rates carry uncertainties, clearly reported and compared across studies. Even at the lower end of estimates, the Phoenix cluster remains exceptional. Its behavior cannot be dismissed as measurement error. You rest with the implications. Efficient cooling supplies cold gas that can condense and form stars. In most clusters, star formation in the central galaxy is modest. In the Phoenix cluster, observations reveal intense star formation linked directly to cooling gas. This connection strengthens the interpretation that cooling flows are active rather than suppressed. You notice how this finding does not overturn existing models but extends them. Feedback still operates in the Phoenix cluster, but it does not fully counteract cooling. Understanding why requires careful attention to energy output, timing, and geometry. You sense that this system provides an opportunity to study cooling and heating in a different ratio, under conditions still governed by known physics. As this realization settles, you become aware that where gas cools rapidly, matter begins to change state, quietly bridging the hot environment of clusters with the cold processes that give rise to stars. You rest with the understanding that stars form when gas becomes cold and dense enough to collapse under its own gravity. This process is familiar on smaller scales within galaxies, but it becomes striking when it unfolds at the center of a massive galaxy cluster. In the Phoenix cluster, observations reveal that this fundamental process is occurring at an extraordinary rate within the central galaxy, far exceeding what is typically seen in similar environments. You begin with how astronomers detect star formation at such distances. Newly formed stars emit strongly in ultraviolet light, while surrounding dust absorbs this radiation and re-emits it in the infrared. Space-based observatories sensitive to these wavelengths measure the total energy output, allowing scientists to estimate how much gas is converting into stars over time. These methods are well tested in nearby galaxies, providing a reliable framework when applied to distant systems. You follow how these measurements show that the central galaxy of the Phoenix cluster forms hundreds of solar masses of stars each year. This rate is not inferred casually. It emerges from consistent infrared luminosity measurements corrected for distance and dust properties. Even when uncertainties are accounted for, the rate remains exceptionally high. You understand that this places the galaxy among the most actively star-forming known at its epoch. You remain grounded in the connection between star formation and cooling gas. The same dense regions identified in X-ray observations as rapidly cooling correspond spatially with regions of intense infrared emission. This alignment indicates that gas cooling from the intracluster medium supplies the raw material for star birth. You stay with the clarity of this link, supported by overlapping datasets rather than assumption. You notice that this behavior contrasts sharply with most central cluster galaxies. In typical systems, star formation rates are low, often only a few solar masses per year. Heating from central black holes usually limits the amount of gas able to cool and condense. The Phoenix cluster breaks this pattern, showing that under certain conditions, cooling can overwhelm heating and drive sustained star formation. You reflect on the physical requirements involved. To form stars at such a rate, large amounts of gas must cool to temperatures of tens of Kelvin, far below the millions of degrees characteristic of the surrounding plasma. This cooling occurs in stages, as gas radiates energy, becomes unstable, and fragments into colder clouds. Observations detect molecular gas within the central galaxy, confirming that this transformation is underway. You remain calm with the role of gravity. As gas cools, pressure decreases, and gravity draws material inward. This inward motion increases density, making further cooling more efficient. The process accelerates naturally until countered by heating or depletion of fuel. You understand that nothing in this cycle violates known physics. It is the scale and efficiency that stand out. You stay with how astronomers estimate the available fuel. Measurements of molecular gas mass indicate that the central galaxy contains vast reservoirs capable of sustaining star formation for tens to hundreds of millions of years. These estimates come from observing emission lines of molecules such as carbon monoxide, which trace cold gas reliably even across great distances. The presence of this gas confirms that cooling has progressed far beyond the hot phase. You notice that star formation also influences its surroundings. Young, massive stars emit radiation and drive stellar winds that inject energy back into the surrounding gas. Supernova explosions follow, enriching the environment with heavier elements. These effects are included in models, but they are insufficient to counteract the cooling on their own. You recognize that while stellar feedback matters, it cannot replace the role of larger-scale energy input. You remain aware that time matters. The observed star formation rate represents an average over recent millions of years, not a momentary burst. The consistency of measurements across different indicators suggests that the activity is sustained rather than transient. This steadiness implies that the underlying cooling process has been active for an extended period. You reflect on how this system provides insight into galaxy growth. Central cluster galaxies are typically large and old, with little new star formation. The Phoenix cluster shows that under certain conditions, even these massive galaxies can experience renewed growth. This does not rewrite established understanding, but it expands it, showing the range of possible outcomes when cooling and heating are not perfectly balanced. You stay grounded in the importance of comparison. Other clusters are studied using the same techniques, and their lower star formation rates confirm that the Phoenix cluster is unusual rather than typical. Its behavior becomes meaningful only in this broader context. You appreciate how careful measurement across many systems allows true differences to stand out. You settle into the realization that extreme star formation here is not an isolated phenomenon. It is directly tied to the cooling of hot gas and the gravitational structure of the cluster. Each piece of evidence reinforces the others, forming a coherent picture built from independent observations. As this awareness gently holds, you sense that such intense growth must interact with the powerful source of energy at the galaxy's center, where gravity concentrates matter into a far smaller, denser region. You rest with the presence of a supermassive black hole at the center of the cluster's central galaxy, not as a dramatic object, but as a measurable source of energy. This black hole reveals itself through radiation and motion rather than visibility. Gas falling inward heats, accelerates, and emits light across radio and X-ray wavelengths. You understand that this activity defines an active galactic nucleus. Its existence is inferred from consistent signals detected by multiple instruments, interpreted through gravity and electromagnetism rather than imagination or narrative. These observations remain stable over time, reinforcing confidence in energy output estimates and physical interpretation across independent observational campaigns. You follow how astronomers measure the black hole's influence without seeing the object itself. Jets of relativistic particles emerge from the central region, detected through radio emission. These jets inflate cavities in the surrounding hot gas, visible as dark depressions in X-ray images. You recognize that forming such cavities requires enormous energy. Calculations show that the black hole releases enough power to affect gas across tens of thousands of light-years, despite its small physical size. Independent measurements confirm this energy transfer by comparing cavity volume, surrounding pressure, and the time required for bubbles to rise buoyantly through the intracluster medium without invoking unknown processes elsewhere. You stay with the understanding that black hole feedback usually regulates cooling in clusters. Energy injected by jets heats surrounding gas, slowing radiative losses. This balance explains why most clusters lack strong cooling flows and intense star formation. Observations show that feedback operates intermittently, turning on and off over millions of years. You appreciate that this timing allows gas to cool slightly before being reheated, maintaining long-term stability. Such regulation emerges naturally from interactions between gravity, magnetic fields, plasma dynamics, and the accretion of matter onto the central object, as supported by simulations and repeated observational comparisons across many well-studied systems throughout cosmic time. You notice that the Phoenix cluster does not fully follow this pattern. Despite hosting a powerful active nucleus, cooling continues efficiently. Measurements show that the energy output, while immense, does not couple evenly to the densest gas. Some regions cool faster than heating can compensate. You remain aware that this conclusion arises from spatially resolved data, not global averages. High-resolution X-ray maps reveal temperature differences on small scales, indicating uneven energy distribution influenced by geometry, timing, and the complex motion of plasma. Radio observations support this view by tracing jet paths that avoid the coolest, densest regions within the cluster core over extended periods. You stay grounded in what is known rather than assumed. The black hole releases vast energy, yet the efficiency of energy transfer matters as much as total power. If energy is deposited too far from dense gas, cooling can persist nearby. You understand that feedback depends on direction, duty cycle, and interaction with existing structures, all of which are measurable. These factors vary between systems, explaining why similar black holes can produce different outcomes without violating established physical principles. In the Phoenix cluster, observations suggest a temporary imbalance rather than a permanent breakdown of regulation within the broader feedback framework supported by comparative studies elsewhere. You reflect on timescales again. Black hole activity fluctuates, while cooling proceeds continuously. A delay between heating episodes allows gas to cool and condense. This timing mismatch may explain why star formation and cooling are observed simultaneously here. You remain calm with the idea that observation captures a phase, not a permanent state. Numerical simulations show that such phases can last tens of millions of years, long enough to be observed but short compared to a cluster's lifetime. This perspective aligns with population studies indicating that extreme systems are rare yet expected statistically within large observational samples of clusters spanning wide ranges of mass values. You stay attentive to how evidence is weighed. No single observation defines the behavior of the central black hole. Instead, radio, X-ray, and optical data are combined. Each wavelength probes different physical processes, reducing ambiguity. You appreciate that this multi-wavelength approach underlies confidence in conclusions about energy balance. Uncertainties are reported openly, alternative interpretations are tested, and models are refined through comparison with other clusters exhibiting both stronger and weaker feedback. This process ensures that explanations remain conservative, grounded in data, and consistent with established theories of black hole accretion and plasma interactions on galactic scales tested repeatedly across independent research groups over many years. You reflect on how this understanding reframes the Phoenix cluster. The black hole is neither absent nor weak. It is powerful, active, and influential. The difference lies in how, when, and where energy is delivered. This nuance helps explain the coexistence of cooling gas and intense activity without contradiction. Such coexistence highlights the importance of spatial resolution and timing when interpreting complex astrophysical systems governed by competing physical processes. It also reinforces the value of studying extreme examples, which clarify mechanisms that operate more subtly elsewhere without requiring new physics or speculative assumptions beyond those already tested extensively by observation and theoretical modeling over decades. You remain calm with the broader implication. The Phoenix cluster demonstrates variability within known laws. It shows that feedback can be imperfect without failing. This realization does not weaken understanding. It strengthens it by revealing range, limits, and sensitivity to conditions. By examining such systems carefully, scientists refine how energy, matter, and gravity interact across scales, improving predictions for cluster evolution throughout cosmic history. This refinement relies on patience, comparison, and the accumulation of consistent evidence, rather than dramatic reinterpretation across multiple observatories, methods, and independent analytical approaches applied to clusters spanning a wide range of properties including mass, temperature, and environment throughout observable space. As this understanding settles, you sense how energy balance shapes everything within a cluster. Heat, gravity, and motion interact continuously. Small differences in distribution lead to large observable outcomes. This quiet interplay prepares attention for how energy balance unfolds across even larger scales. The same physical principles governing this system operate throughout the universe, linking individual clusters into a coherent cosmic framework shaped by gravity and expansion. Observing where balance holds and where it shifts offers insight into the behavior of matter on the grandest scales under conditions measured precisely through accumulated, careful astronomical observation using methods grounded in tested physical theory and reproducible analysis. You settle into the idea that balance does not mean stillness. In a galaxy cluster, energy is always moving, transforming, and redistributing. Heat flows, radiation escapes, gravity pulls inward, and matter responds continuously. When scientists speak of balance, they refer to long-term averages measured across immense volumes and long periods of time. You remain aware that this balance is dynamic, shaped by competing processes that can be quantified through careful observation. You begin with the basic sources and sinks of energy. Hot gas in the cluster loses energy by emitting X-rays. This loss is steady and measurable, depending on temperature and density. At the same time, energy is added through several mechanisms. Matter falling inward converts gravitational potential energy into heat. Motions within the gas generate turbulence. Central black holes inject energy through jets and expanding cavities. Each contribution can be estimated independently, allowing scientists to construct an energy budget grounded in data. You follow how thermodynamics applies cleanly even at these scales. Pressure, temperature, and density remain well-defined quantities, despite the vastness of the system. The gas behaves as a plasma, but its large-scale properties follow equations familiar from fluid dynamics. When pressure balances gravity, gas remains extended. When cooling reduces pressure locally, gravity draws matter inward. You recognize that these relationships hold regardless of scale, linking microscopic particle motion to macroscopic structure. You stay with how energy transport operates. Heat does not remain confined to a single location. Sound waves, bulk flows, and turbulence carry energy across large distances. Observations reveal ripples and subtle fluctuations in X-ray brightness, interpreted as signatures of these processes. You understand that while individual motions are small compared to the cluster's size, their cumulative effect matters over millions of years. You remain grounded in how scientists test whether heating matches cooling. They compare the total power radiated in X-rays with the estimated power injected by black hole activity and gravitational processes. In many clusters, these values align closely when averaged over time. This agreement explains why gas does not cool catastrophically in most systems. You appreciate that this balance emerges statistically rather than perfectly at every location. You notice how the Phoenix cluster challenges this picture without overturning it. Measurements show that, in its core, radiative losses exceed local heating. Energy is present elsewhere in the system, but it does not fully compensate where density is highest. You remain aware that this conclusion relies on spatially resolved data, allowing scientists to examine energy flow region by region rather than as a single total. This level of detail is essential for understanding why some areas cool while others remain hot. You reflect on the role of timescales again. Cooling operates continuously, while heating often occurs in bursts. If heating events are spaced too far apart, cooling can dominate temporarily. You understand that balance assessed over billions of years may still allow shorter periods of imbalance. This perspective helps explain why extreme behavior can be observed without contradicting long-term stability models. You stay with the concept of entropy, a measure of how energy is distributed. In cluster cores, low-entropy gas is denser and cooler, making it more susceptible to collapse. High-entropy gas resists compression and cooling. Observations show that the Phoenix cluster contains unusually low-entropy gas at its center. This property is measured directly from temperature and density profiles, providing another line of evidence for efficient cooling. You remain calm with the idea that energy balance is not uniform across the cluster. Outer regions behave differently from inner ones. Gas farther from the center cools more slowly because it is less dense. Heating mechanisms also deposit energy unevenly. Jets may bypass dense cores, and gravitational heating is strongest where matter falls deepest. You recognize that understanding balance requires mapping these variations carefully. You notice how simulations support this view. Models that include realistic feedback, gravity, and plasma physics reproduce a range of outcomes depending on initial conditions and timing. Some simulated clusters resemble the Phoenix cluster during certain phases. This agreement suggests that the observed imbalance is a natural outcome within known physics, not an indication of missing ingredients. You reflect on how energy balance influences everything else. It shapes star formation, galaxy evolution, and the appearance of clusters across wavelengths. When balance tilts toward cooling, gas condenses and forms stars. When heating dominates, gas remains hot and diffuse. You understand that these outcomes are predictable once energy flows are measured accurately. You stay grounded in how uncertainty is handled. Energy estimates include margins reflecting measurement limits and model assumptions. Scientists explore how conclusions change when these assumptions vary. The persistence of imbalance in the Phoenix cluster across reasonable ranges strengthens confidence in the result. This careful treatment prevents overinterpretation while allowing genuine differences to stand. You rest with the realization that energy balance is not a fixed state but an evolving condition. Clusters pass through phases where heating and cooling dominate to different degrees. Observing a system during one of these phases provides insight into processes that may be subtle or hidden elsewhere. You appreciate that rarity enhances value, offering clarity rather than confusion. As this understanding settles, you sense that energy balance depends not only on visible matter but also on the unseen framework guiding gravity itself, quietly shaping how heat and motion distribute across the largest structures known. You rest with the understanding that much of a galaxy cluster's mass is unseen. It does not emit, absorb, or reflect light, yet its presence is unmistakable through gravity. The motions of galaxies, the temperature of hot gas, and the bending of light from distant objects all point to a dominant component that cannot be accounted for by stars or plasma alone. You follow how astronomers infer this hidden matter from careful, repeated observations rather than assumption. You begin with the motion of galaxies. Galaxies orbit at speeds far greater than can be explained by visible matter alone. Spectroscopic measurements of their redshifts reveal velocities in thousands of kilometers per second. Applying Newtonian and relativistic gravitational calculations, scientists find that the total mass required to keep these galaxies bound exceeds the mass of stars and gas by a large factor. You understand that this discrepancy consistently appears across all massive clusters, forming the basis for the concept of dark matter. You notice how hot intracluster gas provides independent evidence. The gas is held in place by the cluster's gravitational field, and its temperature depends on the depth of the potential well. X-ray observations show that gas moves faster and reaches higher temperatures than visible mass could support. The hot plasma follows the gravitational contours set primarily by unseen mass. This correspondence is measured carefully and repeatedly in clusters across distances and epochs, reinforcing the conclusion that dark matter dominates gravitational structure. You stay grounded in the role of gravitational lensing. Light from galaxies behind the cluster bends as it passes through the gravitational field. This bending produces distortions in observed shapes and positions, measured statistically across many background objects. By reconstructing these distortions, astronomers create detailed maps of total mass, including components that cannot be seen. You recognize that this method depends only on gravity, providing a direct probe of dark matter distribution independent of X-ray or optical observations. You follow how these lensing maps reveal structure within clusters. Dark matter is not distributed evenly. It forms a smooth, extended halo that encompasses the cluster and defines the gravitational potential. The densest regions correlate with the locations of galaxy concentrations and the core of the intracluster medium. This alignment shows that visible matter traces the gravitational framework, but cannot account for its full strength. The consistency between lensing, galaxy motions, and gas properties confirms the invisible mass is real and not an artifact. You remain aware that dark matter does not interact electromagnetically. It does not emit light or heat, nor does it collide like ordinary particles. This presence is inferred solely from its gravitational influence. You find calm in knowing that this inference relies on measurable effects governed by well-tested laws of physics. The conclusion is supported by repeated verification in clusters of all sizes, not just exceptional systems like the Phoenix cluster. You notice that the Phoenix cluster contains an unusually massive halo. Combining lensing, X-ray, and velocity data, scientists estimate total mass in hundreds of trillions of solar masses, with dark matter accounting for roughly 80 to 85%. This estimate is not a rough guess. It arises from independent methods converging on the same result. Such convergence illustrates how multiple lines of evidence strengthen understanding in astronomy, especially when dealing with invisible components. You stay with the realization that this invisible framework shapes the behavior of all observable matter. Galaxies orbit within the potential defined by dark matter. Gas settles and heats according to the gravitational contours. Even star formation is indirectly influenced, as dense regions where cooling occurs coincide with deeper portions of the halo. You understand that the cluster's visible features are organized by an underlying invisible skeleton that dominates the dynamics. You reflect on the timescales of assembly. Dark matter halos form through gravitational collapse, merging smaller structures over billions of years. Simulations of cosmological structure formation, initialized with conditions measured from the cosmic microwave background, reproduce distributions similar to those observed. The Phoenix cluster, while extreme in mass and activity, fits within these simulations as a rare but expected outcome. You remain calm with the knowledge that extreme systems emerge naturally when governed by consistent physical laws. You remain grounded in the methods used to study dark matter. Observers measure velocity dispersion, X-ray temperature, and lensing independently, then cross-check results. When the estimates align, confidence in mass and structure grows. Discrepancies invite closer examination but rarely overturn the overall conclusion. You understand that dark matter is not speculative in this context. It is a measurable, necessary component of the system. You notice how dark matter also connects clusters to the larger cosmic web. Clusters occupy nodes where filaments of dark matter intersect. Gas and galaxies flow along these filaments, feeding growth. The halo provides both a gravitational anchor and a pathway for matter to accumulate. You appreciate that the Phoenix cluster is not isolated, but part of a vast network of structure governed primarily by dark matter, linking local observations to universal patterns. You stay with the idea that invisible matter governs both formation and evolution. Without the dark matter halo, the hot gas would escape, galaxies would disperse, and the cluster would not maintain cohesion. Its existence explains why massive structures persist over billions of years. You rest with the understanding that measurement, not assumption, reveals the framework that dictates behavior on these scales. You reflect on the careful balance between visible and invisible components. While the hot plasma and galaxies are observable, their dynamics follow the contours set by unseen mass. Star formation, cooling, and motion all occur within constraints imposed by dark matter. Observations across multiple clusters confirm this pattern consistently, providing a foundation for interpreting the Phoenix cluster's unusual activity. You settle into the calm realization that the invisible framework, while undetectable directly, organizes matter across immense distances. It provides structure, constrains motion, and shapes evolution over cosmic time. You sense that studying this unseen mass opens questions about how the first clusters formed, how they grew, and how the distribution of dark matter influences observable processes in the largest systems of the universe. You rest with the understanding that observing the Phoenix cluster is like looking back in time. Its light has traveled for over 5 billion years, so you see it as it existed long before the Earth or the Sun formed. Each galaxy, each photon, records a stage of the universe when clusters were still assembling, when cosmic structures were maturing, and when gravity was actively shaping the largest bound systems. You follow the timeline carefully, letting measurement and observation guide your perception of age and evolution. You begin with how astronomers situate clusters within cosmic history. Redshift provides a reliable measure, connecting distance and look-back time. By comparing the Phoenix cluster's redshift to models of the universe's expansion, you understand the epoch in which it existed. Observations of galaxy populations, gas temperature, and total mass reveal the stage of development. The Phoenix Cluster's central galaxy shows intense star formation, indicating that mass accumulation and energy flows are still highly active at this point in time. You stay with the notion that structure grows hierarchically. Small systems form first, merging into progressively larger ones under gravity's influence. Simulations initialized with conditions from the cosmic microwave background illustrate how matter clumps into filaments and nodes, forming galaxy clusters at intersections. The Phoenix Cluster occupies a dense node, having already gathered extraordinary mass at this intermediate epoch. You recognize that the scale of this growth is measurable and reproducible in multiple simulations, confirming that what you see is consistent with standard cosmology. You notice how the cluster's properties contrast with younger clusters at higher redshift. More distant clusters often have smaller central galaxies, less dense cores, and lower X-ray luminosities. These differences are measurable, not assumed, and they provide a baseline to understand the Phoenix Cluster's advanced state. By observing many clusters at varying redshifts, astronomers create a timeline of structural evolution, identifying how mass, density, and cooling flows change over billions of years. You remain grounded in comparisons with older, nearby clusters. These systems often show well-established central galaxies with little ongoing star formation and less efficient cooling. Their hot gas appears more stable, feedback mechanisms have achieved long-term balance, and star formation has slowed or ceased. Contrasting these properties with the Phoenix Cluster highlights how exceptional its central activity is, providing a measured sense of difference rather than exaggeration. You follow how cosmological simulations support these observations. By modeling the growth of clusters over time with dark matter, gas dynamics, and black hole feedback, scientists reproduce a spectrum of outcomes. The Phoenix Cluster emerges naturally as a rare but statistically expected extreme. Its large mass, efficient cooling, and intense star formation occupy the upper end of predicted distributions. You understand that rarity is not evidence of anomaly but a predictable consequence of hierarchical structure formation in a universe governed by known physics. You reflect on how observational cosmology strengthens these conclusions. Deep surveys measure hundreds of clusters at varying distances, each with data on X-ray luminosity, temperature, galaxy content, and redshift. Statistical analysis shows that systems like the Phoenix Cluster are uncommon but not impossible. Its properties lie at the tail of distributions, allowing scientists to place precise probabilities on its occurrence. You remain calm, knowing that rigorous measurement underlies each statement rather than subjective judgment. You notice that studying clusters across time provides insight into feedback processes. Younger clusters often have less established black hole heating, allowing moderate cooling flows. Older clusters show long-term regulation. The Phoenix Cluster occupies an intermediate epoch where cooling proceeds unusually efficiently, even in the presence of a powerful central black hole. Observations reveal both ongoing inflows of cold gas and signs of energetic feedback, highlighting a delicate, measurable interplay of competing physical processes. You stay grounded in what simulations reveal about extreme systems. By initializing models with realistic conditions and allowing gas, dark matter, and galaxies to evolve under gravity and feedback, scientists reproduce clusters with similar properties to the Phoenix Cluster. The simulations predict dense cores, rapid cooling, and high star formation for rare configurations. Observed data match these predictions, showing that even extreme clusters remain within the bounds of standard cosmological understanding. You remain aware that this timeline provides more than description. It informs the physics of cluster growth, energy regulation, and star formation. By placing the Phoenix Cluster in context, astronomers refine models for both common and exceptional systems. You appreciate that each property, mass, temperature, luminosity, star formation, is a measurable clue linking observation to the universe's evolution over billions of years. You reflect on the balance between rarity and inevitability. Clusters like the Phoenix Cluster are rare in any observational sample, yet they emerge inevitably given sufficient cosmic volume and time. This understanding arises from statistics, simulations, and repeated observations rather than impression or speculation. You sense that rarity provides insight, offering a laboratory to explore physics under extreme yet measurable conditions. You settle into the awareness that by studying clusters across epochs, you see patterns that repeat and extremes that test limits. The Phoenix cluster serves as a bridge between early assembly and long-term stabilization, revealing measurable transitions in cooling, heating, and star formation. Its existence illustrates how large-scale structures evolve predictably, yet produce diversity within a framework governed by gravity, thermodynamics, and well-tested physical laws. As this perspective settles, you sense how tracing the cluster through cosmic time quietly invites reflection on the processes that shape other massive systems, linking observation, measurement, and simulation across billions of years in a coherent, measurable history. You rest with the understanding that the Phoenix cluster is exceptional, not by legend but by measurement. Each property that stands out has been carefully quantified, tested against observational standards, and compared across samples of hundreds of clusters. Its combination of extreme mass, bright X-ray emission, rapid cooling, and vigorous central star formation is precisely measured, making it statistically rare yet fully consistent with cosmological predictions. You remain aware that uniqueness is defined by data, not by expectation. You begin with cooling rates. Most massive clusters exhibit suppressed cooling in their cores due to feedback from central black holes. Observations of X-ray spectra reveal that in the Phoenix cluster, the cooling rate in the densest central gas exceeds hundreds of solar masses per year. This value is confirmed through multiple instruments and methods, including emission line analysis and temperature mapping. You understand that this rate is extraordinary, but grounded in repeated and cross-checked measurement rather than assumption. You follow how cooling is linked to star formation. The central galaxy hosts intense starburst activity. Infrared and ultraviolet observations show hundreds of solar masses of new stars forming annually. The spatial distribution of these young stars aligns with the densest, coolest regions of gas. This correlation is directly observed and quantified. You remain calm with the clarity that the cooling flow supplies the fuel, and the resulting star formation is a predictable, measurable outcome of that fuel condensing. You notice the interplay with black hole feedback. In most clusters, energy from the central supermassive black hole offsets cooling efficiently, preventing extreme star formation. In the Phoenix cluster, this regulation is incomplete. X-ray images reveal cavities and jets indicating active feedback, yet dense gas continues to cool and collapse. Observations suggest that energy deposition is uneven, leaving central regions less heated. You understand that this imbalance is not mysterious, but a consequence of spatial and temporal dynamics, measured and interpreted within the framework of established astrophysical theory. You remain grounded in statistical context. While the Phoenix cluster is extreme, it is not unique in principle. Surveys of hundreds of clusters across cosmic time show that very few exhibit comparable cooling flows and star formation rates. Using probability distributions derived from observational samples and simulations, astronomers quantify the rarity of such systems. This approach ensures that conclusions are evidence-based rather than anecdotal. You appreciate that rarity is a statistical property, derived from repeated measurement across diverse environments. You follow how peer-reviewed consensus supports these interpretations. Independent teams have measured mass, X-ray luminosity, temperature profiles, molecular gas content, and star formation rates. All results converge to describe a cluster that is both massive and unusually active in its core. The scientific process relies on replication and verification. It is the convergence of independent observations that establishes confidence in the cluster's extraordinary properties. You sense calm in the reliability of consensus derived from repeated testing. You notice how the combination of factors contributes to its distinction. High central density promotes rapid cooling. Cooling supplies material for star formation. Black hole feedback is strong but partially misaligned. Together, these measured conditions produce a system that stands at the extreme end of known cluster behavior. You understand that each factor is independent yet interconnected, and all are quantified through observation rather than anecdote. You remain attentive to scale. The Phoenix Cluster is among the most massive structures observed at its redshift. Its halo, traced by dark matter, confines both galaxies and hot gas. The total mass, derived from galaxy velocities, X-ray emission, and gravitational lensing, confirms that this is not a small or typical cluster. Its extreme properties are measured across multiple scales, from the central kiloparsec of the galaxy to the millions of light-years of the halo. This multi-scale confirmation reinforces the validity of observations. You follow the temporal aspect. The cluster exists at an intermediate cosmic epoch, more than 5 billion years in the past. Its properties reveal a phase in which cooling dominates over heating in the core, a phase less common in both earlier and later clusters. Observations place it within a timeline of cluster evolution, helping scientists understand how extremes appear temporarily in the context of standard hierarchical growth. You understand that timing matters as much as magnitude in interpreting what makes the Phoenix Cluster unusual. You reflect on measurement techniques. Cooling rates are derived from X-ray luminosities and spectral line analysis. Star formation is measured from infrared and ultraviolet flux, corrected for distance and dust absorption. Black hole feedback is inferred from radio jets and X-ray cavities. Mass and structure are measured through gravitational lensing and galaxy velocities. Each method is independent, but all converge to describe a cluster with extreme cooling and star formation, confirming that the uniqueness is not an artifact of any single approach. You stay grounded in interpretation. Extreme does not mean impossible. The Phoenix Cluster is an expected outlier in the distribution of massive clusters. Its rarity is consistent with simulations and statistical predictions. Scientists are careful to report uncertainties and contextualize measurements. The system is remarkable not because it defies known physics, but because it occupies the extreme tail of known behaviors. You remain calm, appreciating that exceptional clusters provide insight into processes that are subtle in more typical systems. You notice that this uniqueness guides further inquiry. Observations at multiple wavelengths continue to probe the balance between cooling, heating, and star formation. Future instruments, more sensitive and higher resolution, will refine measurements of gas density, jet energy deposition, and molecular cloud distribution. You understand that each new observation will sharpen understanding without altering the underlying physics, reinforcing the idea that rarity and extremity are measurable rather than anecdotal. You reflect on the broader lesson. The Phoenix Cluster's properties illustrate how complex interactions govern cluster evolution. Cooling flows, star formation, and feedback operate together, constrained by gravity and energy conservation. Observations quantify both extremes and averages, demonstrating that clusters follow physical laws while producing measurable diversity. You remain calm, recognizing that the cluster's uniqueness emerges naturally from the interplay of measured forces rather than coincidence. You settle with the awareness that the Phoenix Cluster, though rare, is a coherent and comprehensible system. Its extreme cooling and star formation highlight the limits of cluster behavior while remaining consistent with established cosmology. Its study continues to refine knowledge, providing a measurable laboratory for understanding feedback, gas dynamics, and star formation in massive systems. As this realization lingers, you sense that continued observation will gradually clarify how extremes like the Phoenix Cluster fit into the larger population of clusters, offering insight into both the most unusual and the most typical outcomes in the universe. You rest with the awareness that the Phoenix Cluster is more than a collection of galaxies, gas, and dark matter. It is a natural system governed by measurable laws that extend across billions of years and millions of light-years. Each observation, each spectrum, each image represents a careful interaction between human instruments and the cosmos itself. You follow this connection quietly, appreciating that every measurement reflects both the cluster's properties and the precision of observation. You notice how the scale itself invites reflection. Galaxies orbit at speeds of thousands of kilometers per second. Hot gas spans millions of light-years, emitting energy across the X-ray spectrum. Dark matter dominates the gravitational potential, shaping motions that are detectable only through careful analysis. These phenomena are all measurable and consistent with well-established physics. You remain calm, knowing that understanding does not require imagination, only observation and interpretation through reliable methods. You stay with the interplay of energy and matter. Cooling flows, intense star formation, and black hole feedback interact in ways that can be quantified. The Phoenix cluster exemplifies this dynamic. Dense gas cools, condenses, and fuels star formation, while jets and cavities redistribute energy. Each effect is observed directly. The cluster's behavior emerges from known physical principles, revealing how processes scale from individual stars and black holes to the largest gravitationally bound systems. You reflect on the role of measurement. Every property of the Phoenix cluster, its mass, cooling rate, star formation, and energy output, comes from methods that are repeatable, cross-checked, and independently verified. Gravitational lensing maps total mass, X-ray spectra reveal temperature and density, and radio observations track energy injected by the central black hole. These measurements converge to produce a coherent picture, demonstrating how patient, systematic observation can reveal details about systems billions of light-years away. You notice how statistics and comparison shape understanding. Observing hundreds of clusters at different distances allows astronomers to place the Phoenix cluster within a broader distribution. Its properties are extreme but expected as a tale of natural variation. Rarity is quantifiable, not subjective. By situating this cluster within a population, you see patterns of formation, evolution, and energy balance. You remain grounded in the precision that arises from repeated study rather than speculation. You stay with the subtle lessons of extremes. Studying rare systems like the Phoenix cluster sharpens understanding of universal principles. Cooling, heating, and star formation operate everywhere, but their rates and balance vary with density, mass, and feedback strength. Observing the extreme provides clarity. It exposes dependencies that might be less visible in ordinary clusters. Each measurement reinforces knowledge about ordinary and extreme behaviors alike, showing that science grows by examining both common and exceptional cases. You reflect on time and cosmic evolution. The cluster exists as a snapshot billions of years in the past. Light reaching Earth records a system that has already evolved for a substantial fraction of cosmic history. You understand that by combining data from many clusters at varying distances, astronomers reconstruct the history of structure formation. The Phoenix cluster represents a stage in that history, showing how massive clusters accumulate gas, form stars, and regulate energy over epochs measured precisely through observation and comparison. You remain aware of the unseen framework guiding all visible phenomena. Dark matter halos shape gravitational potential, directing motion and confining gas. Without them, galaxies would disperse, and hot plasma would escape. The structure is invisible, yet its effects are measured directly through lensing, galaxy velocities, and gas behavior. You appreciate that observation, rather than speculation, reveals the presence of unseen components, allowing a coherent understanding of the system as a whole. You notice the balance between simplicity and complexity. Individual physical laws, gravity, thermodynamics, plasma physics, are straightforward and well-tested. Yet the combination of these laws across a system of billions of stars, trillions of solar masses of gas, and enormous dark matter halos produces intricate, measurable patterns. Observations reveal both order and variation, showing that complexity arises naturally from simple rules applied over immense scales and times. You feel calm understanding that intricate behavior does not require mystery, only consistent application of known laws. You stay with the human connection. Instruments, telescopes, and detectors extend perception across light years. Data are collected, calibrated, and analyzed with care. Scientific collaboration allows independent verification. Each observation reflects both the universe itself and the effort of countless researchers working to measure it accurately. You sense that understanding arises through patient interaction between humans and nature, a process that is ongoing and cumulative. You reflect on curiosity and patience. The Phoenix cluster invites questions, yet these questions are addressed with measurement, simulation, and comparison rather than speculation. Observers track cooling, star formation, and energy balance. They examine rare extremes, situate them statistically, and refine models iteratively. This measured approach transforms curiosity into knowledge, allowing the mind to rest comfortably with both the known and the still-to-be-refined aspects of the system. You remain grounded in the evidence. Every statement about the cluster, from mass estimates to cooling rates, is anchored in observable phenomena. Interpretations are tested against independent methods, uncertainties are acknowledged, and conclusions are always conditional on the data. You sense calm in this transparency, knowing that science proceeds cautiously, building understanding steadily, step by step, from measurement to inference. You notice how scale fosters perspective. The Phoenix cluster is immense, yet human measurement makes its properties accessible. Light, matter, and gravity are quantified, linked to universal laws that apply consistently from small scales to vast systems. You recognize that attention to scale allows understanding without overwhelming, connecting the human mind to processes occurring over millions of light years and billions of years. You settle into a gentle awareness that studying such structures reinforces a quiet appreciation for the universe's coherence. Extreme clusters, rare phenomena, and the interplay of heating, cooling, and star formation all operate according to observable, measurable rules. You sense that the act of observation, analysis, and comparison bridges human experience with natural processes far beyond immediate perception. You rest with the recognition that the Phoenix cluster exemplifies the marriage of observation, evidence, and understanding. Its extremes teach about limits, balance, and variability in the universe. Its behavior illustrates principles applicable across scales, from individual stars to massive clusters. You sense that continued study, with ever more precise measurement and refined simulations, will deepen knowledge without altering the foundations already established by careful observation. As this reflection settles, you remain aware that the universe continues to evolve, with clusters forming, cooling, and interacting across vast scales. Observation and measurement connect human understanding to these processes, fostering curiosity tempered by evidence and a calm appreciation for the vast, coherent structures that shape the cosmos.